Okay. We left off the last time. Uh-oh. Come on. It's dead. PowerPoint's dead. Oh, it's back. It's back. No, it's dead. Let me close it and open it back up. We're alive. Okay. We're in the middle of chapter 2. Hopefully, definitely recommend you follow along. Hopefully you're doing it. And we left off here the last time at lossless transmission lines, and we came up with a whole bunch of new equations, but really they're just simplifications of equations that we already had. So some of the ones we ended off getting was that we decided that, well, alpha equals 0. It's lossless, and alpha is an attenuation constant. So that's one of the things we came up with. We also found that beta equals omega square root L prime C prime. Based on that, we said, well, lambda just equals 2 pi over beta. And so that's 2 pi over omega square root L prime C prime. We had Z naught just being L prime over C prime. And we had UP, which was omega over beta. And so we had 1 over square root L prime C prime. So that's where we left off the last time. We went through it a little, we went through it slowly, and we put in the whole equation. And then we said, well, if R prime and G prime equals 0, then it simplifies down to this stuff, basically. It simplified down to these two, and Z naught simplified down to this. And then these ones follow from this beta equaling this thing. And that's where we got to. And we can do one more thing here. I talked before about TEM transmission lines, transverse electromagnetic, and they happen to have this property where all TEM transmission lines have L prime C prime equals mu epsilon. Okay. If you don't believe me, you can go back to the equations that we had, that big table that had coaxial line, 2-wire line, parallel plate line. Along the left, it had R prime, L prime, G prime, C prime, and each one had an equation. And if for any one of those, you multiplied the L prime by the C prime, a whole bunch of stuff's going to cancel out. You're going to be left with mu epsilon. What is mu? The word, very close. All very, very close. Mu is permeability.
It's the mass.
You don't, exactly. Permeability, permittivity. So those pertain to their material properties of the dielectric, the insulator, the stuff between the two conductors, because every type of transmission line we're dealing with has two conductors, an insulator or dielectric in between. Those are material properties of that insulator. So what does that mean? Well, L prime C prime, right? So we got an L prime C prime there. We have an L prime C prime there, and we have an L prime C prime there. So for each one of those, we can replace them with mu epsilon. Okay, so let's do that. So for beta, we have omega, but instead of square root L prime C prime, we have mu epsilon. Beta has units of radians per meter. UP, our phase or propagation velocity, we had 1 over square root of L prime C prime, so we can go 1 over the square root of mu epsilon. So let's play with this one a little bit more. It's in meters per second. Let's just expand this a little bit, and we can say, well, UP equals, let me just erase that, 1 over the square root. So mu equals mu naught, mu r, right? Epsilon equals epsilon naught, epsilon r. Where the naughts, the subscript zeros, are the free space values, and those are just numbers. Those are constants. You can have those written on your formula sheet. They're never going to change. Okay. The R's, the subscript R stands for relative, and that changes for different materials. So I can just write the whole thing out here. Mu naught, mu R, epsilon naught, epsilon R. We are going to make a usual assumption that mu equals mu naught, because most of the materials we deal with, in fact, have that. Mu equals mu naught. In other words, that means mu R equals 1. So what does that do? Well, then that means this equals 1 over the square root of just mu naught, epsilon R. So it just got rid of the mu R. All right, well, what else can we do here? Well, how about this? How about, just for fun, I separate out the epsilon R, okay? So I just pulled them apart, right? That was under there before, I just separated them. And this is useful because this equals something. This equals c, our speed of light. So c equals 1 divided by the square root of mu naught epsilon naught equals 3 times 10 to the 8 meters per second. So that means UP has a really, really simple formula that you can use whenever it's lossless. C divided by the square root of epsilon R. So if I tell you only 2 pieces of information, I tell you it's lossless, and I give you the epsilon R, you know the speed it's traveling at. So if I told you that that's lossless and the epsilon R was 9, what speed, what number, what would the actual value of speed be? Yep. Yeah. And same, so you can always use that, even if, so it'd be, instead of 3 times 10 to the 8, it'd be 1 times 10 to the 8. You can always use this if it's lossless. If it's not lossless, you can't directly use this. It'll give you an approximation, but if, say on an exam, you're not told it's lossless, and maybe it really has some losses, but you use this equation anyway. That happens all the time, by the way, because this is a handy equation. It's nice and simple, right? Easy to use. Well, you'll get some part marks, but you won't get 100%, right? It'll probably be really close though. As long as it's not really lossy, this will give you a quick estimate of what the speed is. Yeah. Well, we're talking about really big numbers, like times 10 to the 8, that sort of thing, times 10 to the 7, times 10 to the 8. So relatively close to that to give you a big ballpark. Definitely not a whole order of magnitude. Yeah, like maybe if it was, you know, a decimal point off, like if it was 1.5 times 10 to the 8, maybe it'd be 1.4 something times 10 to the 8. It totally depends on what the losses are though. So it's hard to say, but normally under most circumstances, it's pretty close. Okay, one last thing we can do here. Our wavelength is equal to UP over F. That's one to remember. We use that one all the time. That's the fundamental one. Well, what could we do here? Well, we have an expression for UP now, right? So we could plug that into there. So if we did, what would we get? Well, we'd get C. I can write it this way. Why did I write it that way? Because, well, we could write it like that and say lambda naught is the free space wavelength. We're not going to use this one too much. Okay, so don't worry too much about this one. It might occasionally pop up, but this one we're going to use all the time. That one's really handy. All right, so as promised, I think the last time, we've got a handy table. Definitely want to include this on your formula sheets. For the exams, what do we have? Propagation constant, that's gamma. I'm about to introduce another thing I'm going to call gamma as well. We'll worry about that later, but this is propagation constant gamma. Yep.
Did you say use the whole table as far as your cheat sheet?
I would
Or
put the
just
whole
some of
table on. You can't go wrong with the whole table. Not a bad idea, but definitely you want this upper half because we have the general case for the propagation constant. It's got the full thing, right? We got the general case for the phase velocity, and we've got the general case for the characteristic impedance. And then we have the special values if it's lossless, which is what we just calculated essentially, okay? Then down below that, basically all you have is going back to the equations that we already saw in that big table, coaxial line, two-wire line, parallel plate line, and substituting in R prime and G prime equals 0, okay? Or using the Z naught is L prime over C prime to get these. So even if you didn't have these, you'd actually be okay. These are handy, but these are the more fundamental ones that kind of apply. You could be really, I'd say 3 ways you could be told that it's lossless. So the first way is if I say it's lossless, okay? And that is going to happen. That might even be the most common. The second way would be if I told you R prime equals G prime equals 0, that's also telling you it's lossless. The third way is if I said the conductors are perfect. They're perfect electrical conductors. Or the conductors have infinite conductivity. That solves half of the puzzle. That tells you R prime equals 0. If the conductors are perfect, R prime equals 0. The G prime equals 0, that happens if the insulator is perfect. Okay, so if I said it's a perfect dielectric or a perfect insulator, or the conductivity of the insulator is 0, that would tell you G prime equals 0. So those are kind of the 3 ways that you could be told that it's lossless and that you could use the second line of equations. All right, so we built up a lot of stuff here. We now have a characteristic impedance. We're dealing exclusively with lossless now for a while. So what does that mean? These equations look pretty familiar. Yeah. Yep. Yep. So that's a 4th way. Yep. Or 0 attenuation. Okay. Yep. We're adding up the ways now. Yep. 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 Any of those things. So what we had before was we had equations that looked a lot like this, but they had a gamma in them. If I go back here, oh no, I don't have any in here. No. So what we had before was like V tilde Z equals V0 plus e to the minus gamma Z plus V0 minus e to the plus gamma Z. So we used to have. And we had the gamma, that's a bad gamma there, but that's gamma, equals alpha plus J beta. Alpha, our attenuation constant, beta, our phase constant, gamma, our propagation constant. So this is for lossless. That means alpha equals 0, which means gamma equals J beta. So we've just substituted in J beta. This is the one we're going to be dealing with. We're going to be dealing with lossless lines for a while now. We're going to deal with this form. It's a little bit simpler. There's no alpha in it. So a reminder what this means. V for voltage, tilde for phasor. Okay. As a function of position, you've got some transmission line. You want to know what the voltage is at some point. I say, what's the voltage right there? Okay, at this point. This equation would tell you. Okay. Tilde means we assume it's AC. Everything's AC that we're talking about. Okay. Everything's AC, everything's sinusoidal, everything's varying with time with some frequency F. Okay. With the tilde, we're in phasor world. So we never write that time dependency. We just know that it's sinusoidal. Okay. It equals two terms. We have the first term, which is the forward traveling wave. The first term describes the forward traveling wave. The second term describes the reverse traveling wave. The V0 plus is the amplitude of the forward traveling wave. It could also have a phase in there, but think about it as just the amplitude. You hook up your signal generator here. You connect it up to this cable. You set it to a certain frequency F. It's a sine wave. You give it some amplitude, 1 volt or something like that. So now you know your V0 plus. It's going down this line. It hits the end, okay? The end is where the load's going to be connected. We're going to have a load here. We got a source here. This equation will allow you to tell at any point on the transmission line what is the total voltage at that point. Made up of two parts because not only do we have that incident wave that comes down, depending on what we've connected here and the properties of this transmission line, we might get a reflected wave. The second part describes the reflected wave. The V0 minus is the amplitude of the reflected wave that's going back to the source. Remember that you can tell the direction of wave propagation by the sign here. Negative J something means it's moving in the positive Z direction. This one, we don't write the plus, but that's obviously what's there. That one's plus. That means it's traveling in the negative Z direction. RZ is increasing in this direction, at least the way that I have it here, okay? J, as soon as you see an E, that's the exponential. The J, that's a complex exponential. Complex exponential, you can use Euler's formula, right? And turn it into coses and sines. When we do that, when we go back to the time domain, we only take the real part. So we're only taking the cos part. And that's the relationship between all that stuff we did before with the time domain waves. We're talking about waves in pool, and we had the cos omega t, minus beta x plus phi 0. The omega t is lurking in the background because we're phasor. The beta z comes from right there, converting this, the e to the j theta equals cos theta plus j sine theta. We only take the real part, so we throw the j sine theta away. We're left with cos theta. So this, we're left with cos beta z, but there's the e to the j omega t lurking back there as well, which gives us the cos omega t minus beta z. And then there could be a phase shift as well. Z is our position on the line, okay? Now, I'd say it makes sense if you were to just ask me and maybe ask you, I think it makes sense to make, if this is the source here, I think it makes sense to make the Z equal 0 right at the source, right? Yeah, we could do that. And then Z would increase. I don't know how long this line is, maybe like 25 centimeters or something, right? So then you could like mark it out with like millimeters all the way along to the end being like 25 millimeters or something like that. And then I could say, what is the voltage at Z equals 20 millimeters? And you'd come along, you'd be like, all right, 20 millimeters is there. You got to figure out what the voltage is there. We could do that, but we're normally interested in what happens at the load. Okay, we're most interested in what happens at the load. The math would be nice if we made the load equal to 0, Z equal to 0. So look at this equation for a second and just think for a second. Z has to increase this way, but the Z's are just relative, right? So we could make this Z equal 0 and this Z equal, I don't know, 25 centimeters or something like that, right? Or we could make this Z equal 0 But Z increasing has to be in this direction. So we can't make this Z equals 25. This would have to be Z equals minus 25 because everything we've done has Z going in the one direction. If we did that, just humor me, if we did that and we were interested in what was happening at the load, what would the voltage at the load be? If we defined the load to be at Z equals 0. What's that?
It's C zero. And we have J gets canceled, then we have J gets zero. Some of the voltage.
Yes. Basically, I think what you said was if Z equals 0, then that's 0 and that's 0. So that makes J beta times 0 equal to 0. J beta times 0 equal to 0. E to the 0 equals 1. So that goes to 1. That goes to 1. So the voltage at Z equals 0, which we've defined to be at the load, is just V0 plus V0 minus. That's nice. We got rid of our E to the J stuff, right? Okay, so that's where we're going to go. So we got two ways, forward wave, reverse wave. We're going to define Z equals 0 at the load, and then we have to go negative though, because we can't change the definition of our direction of increasing Z. Okay, we're going to add in one other thing here. We haven't really talked about D's much yet. Some distance D. So that was nice that we defined the load to be at Z equals 0, but it's not so nice dealing with negative values for the distances and negatives. It's not so nice. So sometimes we'll deal with the Z's. Sometimes we're going to deal with the D's. Luckily, it's a super easy relationship between them. D is just minus Z. So you just flip the negative sign. So how about a picture? Picture's going to help this a lot. We got our source. It has some source impedance. We connect our transmission line right here, okay? Transmission line goes down. A load is connected on the other end. We have defined Z equal to 0 to be at the load because it makes things easier for us, because we're normally interested in what's happening at the load. But if we do that, Z is increasing in this direction. So if our line is L long, well, that means we're back at minus L here. Or we could deal with D's. D is just minus Z. So we're still 0 here because minus 0 is 0, right? But instead of being at minus L here, we're at L. So those are kind of the two scenarios that we're going to go through. All right, so let's see what we got here. An important concept is coming. Ohm's law, V equals IR. Yeah.
They are at the same point and they're not equal.
Same point and not necessarily equal. Yep. Yep, it's a weird one. It's more like you've got a wave coming down, and at this point, you know, it's probably easiest to think about it rather than precisely at the load at like Z equals 0. If you go some incremental value away from it, you could let that go to 0, right? But if you're like a millimeter away from the load, at that point, you still have distinct incident waves and reflected waves. And you could let that point approach, you know, Z equals 0. That's easier to think about it that way than at the absolute Z equals 0 point, because at that point, they're perfectly coinciding and it's the point at which the reflection occurs and things get a little bit fuzzy. So I would think about it the other way, okay? So we have Ohm's law, V equals IR, right? We're dealing with impedances. So let's just use the V equals IZ. And let's say you wanted to solve for impedance. What does this say? It says the impedance whatever it is, this ratio has to hold, right? The voltage across the impedance, that's the V, divided by the current through the impedance equals the impedance. Okay, that's basically what it says, this relationship. And it's easy to think about that with resistors, right? Because R equals V over I, you put some voltage across it, and the ratio of that voltage to the current through it, that is the resistance, right? Okay, what would someone translate that for me to the symbols that we're using on here? If we're dealing with ZL. So if we're interested in a relationship for ZL, what voltage and what current, what symbol would it be? Yeah, it'd be VL tilde, because that's the voltage across ZL over the IL tilde. Okay. All right. Well, we know what VL tilde is. We already did it, right? VL tilde, what is that? Well, that is V tilde at Z equals 0, because we defined the load to be at Z equals 0. So what is that? Well, we plug in Z equals 0, which we already did. It's just V0 plus V0 minus. So we've just got the top one. What if we did the same for the bottom? IL tilde, I tilde at Z equals 0. Let's pop back here. Very similar, right? They both go e to the 0. E to the 0 is 1. We're left with V0 plus over Z naught minus V0 minus over Z naught. Okay. So V0 plus over Z naught minus V0 minus over Z naught. Okay. So that's good. What is our ZL? Well, it's the ratio of those, right? So what do? We would divide those. Okay. VL over IL is this one over that one. Now they don't cancel out, right? Because we got a plus up here, we've got a minus down there, right? Now Z naught's on the bottom of both of these, and it's in the denominator of the denominator, so it goes upstairs. Okay, so what are we left with here? We're left with ZL equals, well, we still have our V0 plus V0 minus, and we have our denominator V0 plus minus V0 minus, and the whole thing is multiplied by Z naught. Now this is fine. You can say, all right, well, you know, I guess this is something. But normally we probably know ZL, but what we don't know probably is like V0 minus, right? We might know V0 plus, because if you got the source and you've set like what the amplitude is, and you know what it's connected to, and you know what V0 plus is, that's the amplitude of the incident wave. You probably know Z naught, because what Z naught? Well, Z naught is that equation, right? If we're thinking lossless, it's even easier. It's just L prime over C prime, the square root of L prime over C prime. And you could say, well, what's L prime and C prime? And you go back to your equations and you go, oh, those equations just have the material properties in them, the mu's and the epsilons, right? That's the stuff that the transmission line is made up of, the material properties of it. And it's got the dimensions in it. Like for coax, it's got the little a and the little b, which are the radii, right? For the 2-wire line, it's got the little d and the capital D, which are like the diameter and the space in between them, that kind of stuff, right? So basically, this one's entirely determined by the material properties and the dimensions of the transmission line. This one, if you have control of the source, you control that one. This one is whatever you're connecting it to. Often you know it, but we don't really know much about the V0 minus yet. So let's say you wanted to solve this thing for V0 minus. How would you do it? It wouldn't be that hard. You could multiply through by the Z0, right? And you could maneuver things to the left and right and get common denominators if you wanted to, and then like factor out your V0 minus and divide by the rest of the stuff, just the usual stuff, right? So if you did that, you'd get something like V0 minus equals ZL minus Z0 divided by ZL plus Z0 times V0 plus. Now this is interesting, right? This says, remember what V0 minus is? What is that thing again? And what about the reflected wave? Like what? It's the amplitude. Think about it as the amplitude. That's, and I say amplitude a lot. Technically, there is a potentially a phase shift in there as well, but it's much easier in your minds if you think about it as the amplitude, okay? The amplitude of the reflected wave equals something times the amplitude of the incident wave. This something determines how much gets reflected. And we can define this thing called capital gamma. It's called the reflection coefficient, which is this thing. So its definition is V0 minus divided by V0 plus, and it's ZL minus Z0 over ZL plus Z0. And we are going to use this thing like crazy. I would use exactly, this is exactly the form that I always think about it as, okay? So I have it repeated on the next one here, right here. This tells me the symbol capital gamma. Now, I'm just going to say gamma, which could maybe be a little bit confusing because I also say gamma for the propagation constant. But they're two totally different things, though they are related. Gamma is the symbol for the reflection coefficient. This here, you're rarely ever going to use that to calculate something, but it always reminds you of the definition of this thing, okay? You got two waves, some incident wave amplitude, some reflected wave amplitude, the ratio of the reflected wave amplitude to the incident wave amplitude. So from that, you could say, well, what would gamma be if there was no reflected wave? What would the reflection coefficient be if there was no reflected wave? It'd be 0. If there's no reflected wave, then V0 minus is 0. There's no amplitude of it, right? What would the reflection coefficient be if everything was reflected? The entire incident wave got reflected. What would the reflection coefficient be? It'd be 1. Could you have a reflection coefficient of 2? Why not? Because of which, sorry? Yep. Can you think of another reason? More like physical, like exactly. Yeah. Now, if you had active circuits involved, like transistors and all that kind of stuff, well, then all bets are off. I mean, you can have negative resistances and you could be adding in power from DC sources and all that stuff. But everything we're dealing with is just passive, meaning no power sources, resistors, capacitors, inductors, that kind of stuff. Our reflection coefficient will always be 1 or less, okay? The magnitude. I never think about it in terms of the current. I always think about it, so I wouldn't worry about that one too much. I always memorize this because symbol, definition, and the equation that you're going to use. This is what you're going to actually use to calculate it, okay? You could divide top and bottom by Z0. So if you divided that by Z0, you'd get, well, that divided by Z0. And if you divided that by Z0, well, Z0 divided by Z0, you'd get 1. You could do the same thing for the bottom. And then you could define this thing as the little guy, little ZL. We're going to do that later, but I wouldn't worry about that too much for right now. It's called the normalized load impedance when you divide the load impedance by the characteristic impedance. When we hit Smith charts, we're going to do that. For now, I recommend that you just think about it in terms of this. They're all equivalent, okay? It doesn't really matter, but I think it's easier to use that one. So, important to remember that gamma, the reflection coefficient, is a complex number in general. What does that mean? It means it's got a magnitude and a phase, if you think about it in polar form. So remember, we got rectangular form of complex numbers, we got polar form. Rectangular form is real plus j imaginary. Polar form is magnitude, angle, something. We're normally going to think about the reflection coefficient as magnitude, angle, something. And if it makes you feel better, it's perfectly fine to write it like this. If the e to the j scares you a little bit, okay? Feel free to write it like that. Basically, every midterm 1 and final exam part 1, anytime I ask for the reflection coefficient, here's the situation, find the reflection coefficient. Some students will just give the magnitude of gamma. They won't give the theta r, which is the angle. So you only get half marks because you only calculated half of gamma, right? The reason why that often happens is because we're really concerned about the magnitude of gamma, because it tells you how much gets reflected, the magnitude of how much gets reflected. The phase shift just kind of like, it tells you other things like how it, well, what the phase shift is, where they constructively and destructively combine, but we're often pretty concerned about that, which is why it's easy to forget about the phase angle. So just always remember, if you are asked for gamma, magnitude and phase, there's no units to it. You could tell that from the equation in the top right. We got ohms over ohms, okay? It's just a coefficient of how much gets reflected. Let's look at the equation and imagine ZL equals Z naught in the top right. 0. Gamma equals 0. And if gamma equals 0, we already saw, right, that V0 minus equals gamma times V0 plus. So that means when ZL equals Z naught, the numerator goes to 0, which makes gamma equal to 0, which makes V0 minus equal to 0, which means there's no reflected wave, which is often what we want. This is called matched, when you have a load that's matched to the line. Later on, we're actually going to go to have cases where it's not matched, and we have to create a matching network. We have to add something in there to make the thing that we put in, together with whatever the load was, that whole combination, we make it look like Z naught, so that our new combined ZL equals Z naught, and there's no reflections. So that's down the road when we get to Smith charts. This is the match condition. You'll often hear people talk about it, whether it's matched or not. So that's what it means. Whatever the Z naught is for the transmission line that you're using is equal to the ZL that you're connecting at the end of that transmission line. All right, what if you didn't connect anything? Imagine there's a source here and I've connected it up. I just didn't connect anything. What do you think is going to happen then? Yeah. So this is, if you don't connect anything, that's an open circuit, right? An open circuit is really when you have an infinite impedance. It's not connected to anything, right? So that would be an open circuit. ZL equals infinity if I just didn't connect it to anything. So look at our equation, ZL equals infinity. Infinity minus, I don't know, for this it's 50. So infinity minus 50 over infinity plus 50. 50 is pretty small compared to infinity, right? So it's 1. It's just equal to 1. A reflection coefficient of 1 has V0 minus equals V0 plus. Everything gets reflected, okay? So that's that one. What about a short circuit? So what would a short circuit look like for this? Well, you got the pin in the middle, right? And you've got the second conductor is around the outside. If you put some kind of a cap on it that directly connected the center pin to the outer shell, that would be a short. A short is a load impedance of 0. So if you look at our equation, with ZL equals 0, 0 minus Z naught divided by 0 plus Z naught, well, that's just minus Z naught over plus Z naught. That's minus 1. So the magnitude of minus 1, that's 1, right? Magnitude is like absolute value. So the magnitude of V0 minus is equal to the magnitude of V0 plus, but there's a phase shift. The minus sign is like a theta R of 180 degrees, okay? So it's just that phase shift there. So the amount that gets reflected is the same, there's just a phase shift. Here's a table. I wouldn't worry too much about this one, just the main ones here that we've been talking about. I wouldn't worry about that. I don't think you'll probably never use that equation or these ones down here. But when the characteristic impedance of the transmission line is equal to the characteristic impedance, is equal to the load impedance, you have no reflection. If it's a short or an open, the magnitude is equal to 1, but it's either 180 or 0. Okay. Yeah. The it's irrelevant. It's all 0. Yeah. That yep. So hopefully you're reading, following along in the book. Do examples 2, 3, and 2, 4. They're good ones. And let's do an example here to put some numbers to all this stuff. Okay. All right. How are we doing on time? 6:16. So I guess we have a half an hour, right? All right. A 50 ohm transmission line is connected to a load consisting of a 30 ohm resistor in series with a 331.5 FF capacitor. Find the reflection coefficient at the load for a 2.4 gigahertz Wi-Fi signal. We have some transmission line. At the end of it, we've got this RC series combination. I could have not said that, okay? That would be totally fair game on a midterm or final. Just saying a 50 ohm transmission line, that's how people talk about this stuff. They don't say a transmission line with a characteristic impedance of Z naught equals 50 ohms. Okay, people are just gonna say 50 ohm transmission line, and you need to know that that means Z naught equals 50 ohms, okay? We have a load that's a resistor in series with capacitor. We want reflection coefficient. That's capital gamma, okay? The equation that I always remember for capital gamma, ZL minus Z naught over ZL plus Z naught. We know Z naught, it's 50. We need ZL. What's ZL? Yeah, yes, this is another place where almost without fail, if I give a question like this on a midterm, somebody messes up the impedance of the capacitor, okay? So I'll just write it. So it'd be RL plus 1 over J omega CL. And just to remind us, the impedance of a capacitor is 1 over J omega C, or if you like, minus J over omega C. Whenever you flip the J from the bottom to the top or top to the bottom, you just have a negative sign in there, okay? So it is not, ZL equals 30 plus, I don't know, J331.5 or something like that. It's an impedance. It changes with frequency. You have to have it in there. For a capacitor, it's 1 over J omega C. What is it for an inductor? Yeah. So make sure if you're ever given the equivalent circuit with capacitors or inductors, you use their impedance. We are talking about an impedance, okay? ZL. So let's do it. So let's find I'll call it ZCL for the impedance of the load capacitor. So it's 1 over j omega c. So 1 over j. So what's omega? Yep. 2 pi f times our c, 331.5 times 10 to the, think about it, because you could be faced with this on some 50, okay? Femto. The little f is femto. So it goes milli, micro, nano, pico, femto, and we're not really going to go beyond that, okay? On the upside, you got kilo, mega, giga, tera, right? We won't usually go much above giga, maybe occasionally tera, but most people know tera because it's like terabyte and that sort of thing, right? But femto, you don't use femto all that much, so make sure you know what that is. So all this is in the denominator. So can someone punch that in? I'll bring the j upstairs, so it becomes minus j. And so the rest of it is really just 1 divided by 2 times pi times 2.4 times 10 to the 9 times 331.5 times 10 to the minus 15. $12.57. Let's see if anybody else gets the same thing. $200. Anybody else get? Anybody else get anything? Confirmation of one of the answers? Okay. So minus j times 200. Just double check it if you didn't get that. All right. So our total ZL is 30 minus j 200 ohms. Now we're ready to use our gamma formula. All right. So we just got to plug it in for our ZL. So let's do it. Gamma is ZL minus Z naught over ZL plus Z naught equals 30 minus J 200 minus 50 over the same thing, but plus 50. We can add the reals. Okay, not much we can do with the imaginary, but we can add the reals together. So 30 minus 50, negative 20, minus J 200, divided by 30 plus 50, 80 minus J 200. What do we do now? How can we handle this? What's that? Convert to polar. Yep, that's a good idea. Maybe you have a calculator that can just do this. That'd be nice, but let's convert to polar because then it makes the division easier. So we are going to have something over something. Can someone give me the magnitude of the top? So we're converting from rectangular form to polar form. We're going to do the top one first. And I want the magnitude, just the magnitude. 200 and 200, 201 or 200? 201. Okay. So 201 angle something. What's the magnitude of the denominator? Hang off on that one just for a second. We're gonna fight it out with the angle in a second. I'm just gonna get the magnitude of the denominator because I think we'll get. Sorry, what was that? Sorry, 215. 215. Great. That 215. Okay. Let's do the angle of the top one. Let's do it in degrees. So we want the angle of minus 200 minus 20 minus J200 converted to polar form. What is the angle of that? So I've got an 84 and I've got a minus 64. We got a plus 84 and a minus 84. Okay, do we have anybody else? All right, let's see if we can get agreement on what quadrant we're in. So let's say we had our quadrants. The X is the real, the Y is the imaginary. I'm going to call this quadrant 1, 2, 3, 4. So which quadrant are we in? Okay. Now, let's just say we forgot this business of quadrants. Let's not say we totally forgot the business of quadrants. Let's say we did think about this, that we're in the third quadrant, but we couldn't remember the business of this stuff. I remember sometimes you got to add stuff and minus stuff. Let's just say you went with your answers, either plus 86 or minus 86. Is that what it was? 84, 84.6 or something. Does that check out? Does that agree with what quadrant we're in? Right, because 0 starts here and goes up like that. So plus 84 or plus 84.6 would be like pretty much like close to there. We'd still be in quadrant 1 though. If we had minus 84, then minus we go clockwise and we'd be in quadrant 4. So we know, oh, I can't trust my calculator here. I gotta add 180. Okay, we still have the business of plus or minus though. Anybody else calculate anything? So it should be you do minus 200 divided by minus 20. You got a minus divided by a minus, so that becomes positive, which is the source of this ambiguity about the phase angle. Because if you compared that to, if it was plus 20 plus J200, you'd still have 200 divided by 20. You'd get 10 in both cases. This is why there's that ambiguity. But in any event, you do minus 200 divided by minus 20, you'd get 10. You do inverse tangent of 10. Make sure your calculator's in degree mode. I think it'd spit out positive. Okay, it'd spit out positive 84.6 or something like that. Then you'd have to add 180. Yeah. Yeah. So that would be something, I think, like 264. Somewhere in that neighborhood. Okay, what angle do we get for the bottom one? Okay, we got a negative 68. Let's see if that makes sense. Let's say you punch it in your calculator, that's what it spit out. So you're 80, so your real part's positive. That means you are on the right side of this. Imaginary is negative. That means you're in the lower half of it. So you're in quadrant 4. You got minus 68 or something like that. Minus 68 would land you in quadrant 4. So you're okay. You don't have to do anything with 180 because the value your calculator gives you actually corresponds to the quadrant that you're in, because it was minus 68 or something like that. What's that, sorry?
1 and 4 is okay.
Yeah, exactly.
But not 2 and 3.
Exactly.
Because,
Yep.
because it's possible.
Yeah. Yep. So we're okay with the minus 68. How do we do it now? Everything's fun. Everything's easy now. That was the only tricky one there. So how do we do this? Just mechanically, how do we? Yep. So you divide the magnitudes and then you go that angle minus that. So it'll be 264 minus 68. So that'll come out to something like 0.9 something, maybe 9.3. An angle would be like 3 32.5. Now you could have also, you can always add or subtract 360s, right? Because it's one full rotation. So 9.3, if you subtracted 360, you get 27.5 degrees. Normally the reflection coefficient is always given in left and polar form, as I said before, because look what that tells you just by looking at that. That's like 93% of that incident signal's amplitude is getting reflected back. Oh, yeah, minus 27.5. Yeah, so most of it's getting reflected. This value, this gamma, this reflection coefficient is used all over the place in the RF and microwave world. You get any kind of component or device or an antenna, you look up the data sheet and it would give you the value of gamma, or you would need to measure the value of gamma. If you measured the value of gamma, the way you do it in a lab is you would use a piece of equipment that, unless you're taking the 370 lab, you probably haven't used yet, unless you work in industry somewhere. You'd use a vector network analyzer. So it's called a VNA. And it works based on waves, exactly like what we've been talking about. So there'll be an incident wave. It knows what the incident wave it sends out is, and it measures how much gets reflected, okay? And so for like an antenna is an easy one to think about. You want that to be a low number, because you can imagine if you have a transmission line and you connected an antenna to the end of it, and you send a wave down this transmission line and not very much bounces back. In other words, you have a really small V0 minus, not very much bounces back. Had to be radiated. Where else could it go, right? Now, if you had a lossy antenna, it could go in losses in the antenna. But if you assume for the time being that it's just like a metal antenna, there's not much losses, a low reflection coefficient means it's been radiated, the power's been radiated. All right, so we have 15 minutes to go. Yeah.
So the positive side of the answer is, did you want that too as well?
No.
as the-
Either one is correct.
you know,
Yeah, because it's all just a circle, right? Whenever you have an angle like that, it's always just add 360 minus 360. I think the book might like, I think it says for certain definitions, it wants it between plus 180 and minus 180. I'm not going to be too picky. Like if you gave either one of those on an exam, I'd give you full marks for it. Yeah. Okay, so we got like 13 minutes left. And we're about to go through a bit of a heavy, ugly equation. But before we do, I think it's useful if we watch some videos to see,
can we choose?
to watch videos or do it. We got to do both. We're going to do both. I guess if one's optional, it's the videos that are optional. So I think we'll watch some of the videos, which will close off tonight. We won't get through them all. We'll be in the middle of them. And then we'll come back on Wednesday and we'll go through the math. And then we'll finish off the videos. So you'll kind of like get a bit of a feel for what we're talking about, jump into the math, and then watch some more of the videos, okay? So the idea here, what we're talking about, we got a reflection coefficient. Reflection coefficient is you have an incident wave. The incident wave hits some load. Depending on what the load is and what the characteristic impedance of the transmission line is, you might get a reflection back. Let's assume you do get a reflection back. It's not like you just sent a few waves down here and then those few waves are reflected back. No, you're just continually sending waves down here. So you got all these waves, they continue to come, they continue to come, incident waves. All of those waves get reflected. So those waves just keep going back, keep going back. We have interference. We have constructive and destructive interference between the incident waves and the reflected waves. When you have these waves going in two different directions, they add together. It's a principle of superposition. And you get areas where they add together to create bigger peaks, constructive interference, and you get places where they cancel each other out, either partially or completely with destructive interference. It's like if you've played around in the water in the pool, I think we might have talked about it before, where you're in a pool and you have like an inflatable raft or something and you're making waves and you've got someone else on the other side of the pool and they're making waves. You'll see these crazy like spikes in the waves and valleys and that sort of thing where the waves add together constructively and destructively. The same thing happens on the transmission lines, which is really important because, well, for a lot of reasons, one of which, imagine if you had a good amount of power in this. Like you're sending high amplitude waves down the transmission line, and a lot of that gets reflected. Now you'll get places on the transmission line where they add together. You could get even bigger spikes of voltage or power, and you could damage your transmission line. If you're connected to some electronics, some transistors over here, if there's a peak near those, you could damage the electronics. So it's a really practical, really important concept. So let's watch some videos and let's start off with a simple string.
So what we have here
Give me
is
a
a
second
frequency
with the
generator
volume here.
connected to what's called a wave driver. It's just a speaker. It's going to pump
That's so
up and
funny.
down at whatever frequency
right.
I set this guy to. When this guy pumps,
Hear it, no one else could. Okay, give me a second. And what did you say, sorry?
Damage electronics means device is damaged.
Yeah, really what I'm talking about is like the transistors. You could exceed their operating voltage levels, and so you could burn them out. Yeah, when I was in, before I came here, I worked in the Department of National Defense in Canada, doing electronic warfare stuff. And so it was high power stuff. And one of the things that it was like a backpack war thing. And one of the warnings on it, the big warnings for the military guys who are using it was, do not power this on with an antenna not connected. Like make sure the antenna is connected before you power this on. The reason why is it's a lot of power. If no antenna is connected, it's an open circuit. It's an open circuit. Your gamma equals 1. Your V0 minus equals your V0 plus. Everything's getting reflected. You're getting these peaks and these nulls, and that could damage the electronics that originally, as it comes back. Yeah, yeah. Okay, let's see if we got some volume now.
up and down, well, he sends a wave.
All right, we're gonna have to do it
Sends
this
a
way.
wave down to this end, the wave reflects,
What's that?
comes back. Now, if I set it to
Yeah.
just any old frequency, let me just turn this
No.
on.
Give me a second
no,
here.
it's still a little higher. So it's sending waves back and forth,
This is
but
quiet.
these waves
I
are
did this
out of
in the
sync,
other
if you
room.
like.
And it
They're,
was
they're
okay. Mute, start video, more. Okay, let me go back. Oh, not that. There.
They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have
In
what's
the other
called
room,
a
the setup's
standing
exactly
wave.
the same. And
That
it was
is
smart enough to
The
rev the
wave
audio up there.
that's sent down and
Okay, we're gonna have to do
reflects
this way.
constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down.
So quiet.
And we'll see that in a second with the high-speed camera.
Well, we've only got 5 minutes left, so I may have. No,
So
I
here
can
we
hear it
have what's
actually.
called the second harmonic.
I don't know. I have my
It's
iPad
the
cranked
second
too.
possibility for a standing wave
I don't know why
for a
it's quiet,
string
but
that's held at both ends.
yeah, I
So
gotta put
notice
them in
this is
there.
a node.
all right. Well, I
This
may
is
have
a
to sort
node,
this out for
and the
next
middle's
time.
a node. So we have 3 nodes for this wave. Now,
I think
like I
it probably
said, second harmonic. Well, what's the first one? The first one will be half this number, so 8.5.
It's on.
Mute is on.
And there we go.
Is on.
Still say mute is on?
Now we don't see a picture.
It's basically the scenario of a jump. Now,
Well,
I can find
maybe it
any of
was
the other
not meant to
all of
be.
the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times
I don't
8.5.
care so much about this video, but the other video is really,
25.
really good. So we've only got 5 minutes left. So how about I just start to talk about the equations? I'll figure out the videos, and then next time we'll watch the videos with some sound. Okay. So, yeah, that's a good point. Why is the screen on now?
Unmute. Where's the bottom yellow button? Yeah. Yeah, there we go. It was. It was. Maybe it wasn't meant to be.
We're back. All right. Well, I'll sort that out for Wednesday. So, what do we got here? We got a bunch of equations. Top ones are familiar, right? We got gamma, that's our reflection coefficient, our definition of gamma. These are minus or these are plus. This is the one you're actually going to plug numbers into, just like we just did in the example. Right? If you remember this one, then you can always just rearrange to get this one. Okay? You just go, well, I'm just going to bring that one over there, and I can calculate V0 minus as long as I know gamma and V0 plus. Okay. So step one for us, well, that's the same as what we saw before. That's where I basically said at the beginning of tonight, like, we're going to say the load is at Z equals 0. So we can plug in Z equals 0, and that goes away, and that goes away, and we have V0 plus plus V0 minus. Okay? It doesn't have any gammas in it because we are lossless. Okay? So that's why we've only got the J, beta, Z in there. All right, well, what could we do here? Well, we could say, well, V0 minus equals that thing, right? So I could write this as V at Z tilde V0 plus e to the minus J beta Z plus gamma V0 plus e to the J beta Z. We can factor out the V0 plus. That's that. So we went from there to there. All we did was plug in the V0 minus equals gamma V0 plus, and then factor out the V0 plus. We could do the exact same thing for the I. Okay. Now's where it gets a little ugly. Okay, what's going on here? Well, what we're trying to do is we want to know what's going on with these waves interfering with each other. That's really the question we're trying to answer. We've accepted we have an incident wave. We potentially have a reflected wave. We want to know something about how they're adding together and interfering with each other. And the way we're going to determine that is with the magnitude. Okay. So we're going to figure out what the magnitude of the voltage is. Why that? Well, at some places they're going to add together constructively, like I was saying, and in others add together destructively. In those cases, if we're looking at the magnitude, instead of the absolute value, because it's the waves are moving, right? They're going to be adding together, and then they're going to be canceling each other out. We want to look at the magnitude to determine the standing wave pattern. So next time when I get the video working, we're going to see examples of standing waves. Standing wave is just a fancy way of saying you got two waves, they're traveling in the same medium, they're interfering with each other. They're going to create these patterns. So for instance, you see standing waves in water, like I was saying before. We're going to see them on a string, a place where you maybe don't realize it, but they're standing waves is in your microwave at home.
Your microwave is a box that injects high power microwaves. That's why it's called a microwave. At 2.45 gigahertz. It injects it in there, and your microwave oven is a metallic cavity. That's why, like, when you look through the door, you see there's like a whole bunch of like little holes, but mostly it's metal. It's a screen. Those holes are much smaller than the wavelength of the signal. That's what makes it so it has some shielding effectiveness. So, and you can figure out now, you know how to calculate its waves in air, right? So we know the speed. Waves in air, just like light, speed of light. So lambda equals c, because we're in air, divided by f. C is 3 times 10 to the 8. F is 2.45 times 10 to the 9. You could get a number for that. Whenever you have screening, you want to make sure that the gaps in your screen are much smaller than the wavelength. So you inject these electromagnetic waves and they bounce all around in there like it's chaos, right? You can't see it, but it's chaos. In some places, they add together constructively. In some places, they cancel each other out and they add together destructively. If you ever have an old school microwave that doesn't have the rotating thing, you might find that you put your food in there and there's some places that burn your mouth and other places that are still like cold.
So is that where the canceling comes?
Exactly. And that's why you turn it. So the food rotates through the hot areas and the cold areas, the peaks and the valleys. So the electromagnetic energy gets absorbed mostly by the water that's in the food. So the power gets absorbed there, which turns into heat. And if you're rotating it, then you can get a more uniform temperature throughout it. So those are standing waves as well. So it is now 6:46. So I'm going to get this sorted out, and we'll start off by probably watching some videos when we come in on Wednesday. Okay.
Tell my family, oh, this portion of the food is cold. Well, that's because